Well, thank you very much for inviting me to talk. I'm not quite sure whether this is... I can't say with any kind of confidence that this is of sort of interest to model theorists. But I have a little sort of hunch that there might be elements of what I say that, or that there might be some sort of fruitful results if model theorists were to sort of pile into this particular area. So, but that's a sort of wild speculation rather than said with any kind of genuine understanding of model theory. I think I'm going to start just by explaining the different words in the title. So I'll start with the U4 norm. What is the U4 norm? And in fact, I won't even start with the U4 norm. I'll start with something called the U2 norm, because the U4 norm it's sort of painful on the arm to write out. But if I tell you what the U2 and U3 norm is, or are, I mean, then you can work out the U4 norm for yourself. So the U2 norm is defined as follows. I've got to explain what this symbol means as well, but so what have we got here? F is a function, I should have said this before, I suppose, from a finite abelian group to complex numbers. And this just means the average over all x, a, and b in the group. So we take this thing, which is a sort of average over all. I sort of think of them as squares, but they're really more like parallelograms or something. So we've got an x and an a and a b. And then we take the average over 4 points, and we put in complex conjugates according to the parity of the number of a's and b's that we've chosen in each term. It's not completely, I mean, it doesn't just sort of immediately jump out from the definition that this defines a norm. In a moment we'll see why it does define a norm. But anyway, that's the U2 norm, but it is a norm. Okay. And then the U3 norm is defined by the formula. It already gets a little bit more. I'll do this one quickly, and then I'm just, after this is the last one I'm going to write out in full. Had a bit of practice at that over the years. So again, we just take all possible choices of either we pick an A or we don't pick an A or we pick a B, blah, blah, blah. Put a complex conjugate in if we've got an odd number of things that we've chosen. And then take the 8th root of the average of all those, which is now an average over three-dimensional, I mean, again, we sort of call them average over cubes, so they're more like parallelopipeds. And that also defines a norm. And I won't tell you why that's a norm, but it's an exercise, not a completely, well, it's not a completely, I guess it's sort of less straightforward than this because there's a cheat that I'm going to show you for how to show that that's a norm, which is not available here, but there's a different way of doing it. Roughly speaking, you prove a sort of generalized Cauchy-Schwarz inequality for this. So if you've got different f's here, then this thing is less than or equal to the product of the norms of all the individual f's. And once you've got a generalized Cauchy-Schwarz, then the same proof that goes from Cauchy-Schwarz to Minkowski in a Hilbert space goes from this generalized Cauchy-Schwarz to a sort of Minkowski or triangle inequality in the U3 norm. Now, so the U4 norm, obviously, you just stick in a D, double the number of terms. You can see why I wasn't prepared to write it out, and etc. You get UK norms. So that's that. What about inverse theorems? Well, first of all, there's one reason that these things are useful and why they came up. They came up when I was proving, a depressingly long time ago now, giving a new proof of Szemerédi's theorem. And if I just write out, well, supposing we've got some functions fi, and they're bounded. Additive combinatorists, when they say that a function is bounded, it's defined on a finite set. So you might say, well, of course, all functions are bounded. But what we may mean that is a sort of quantitative notion of boundedness. It means it takes value at most 1. or it's sort of morally equivalent to being uniformly bounded as the size of the group tends to infinity, but we might as well make the uniform bound equal to 1. And then we get the following inequality that may look sort of suggestive. That thing here, which is a sort of average over arithmetic progressions of length k of a product of the different functions, is at most it's at most the largest of the UK minus 1 norms. So what that says is if one of these functions at least has a small UK minus 1 norm, then the whole of this average has to be small. And the way to think about this is as a sort of quasi-randomness condition. So if f, saying that the UK norm is small is saying that f is somehow random enough that you get lots of cancellation in these kinds of expressions. And it turns out that that cancellation, again, just the proof of this is just uses a lot of a sort of iteration of the Cauchy-Schwarz inequality. I put sort of a mod sign around here. So this is why it was relevant to Szemerédi's theorem. So what one can show, and again, another thing is that if we've got a set, so a subset of a finite abelian group, it's called A, and I have the bad habit of when I have a subset of an abelian group, I write AX to mean 1 if x is in A and 0 if it's not. So A and its characteristic function have the same symbol. So if A has density alpha, then and let's say, well, one can show that the UK norm of A has to be at least alpha. That's another Cauchy-Schwarz proof. With near inequality, sorry, near equality, I beg your pardon. So if it's only just bigger than alpha, implying that this expression here, the sort of average over arithmetic progressions, is roughly what you expect. So it's approximately equal to alpha to the k. So when would it be alpha to the k? If A was a random set and you just chose an arithmetic progression at random, then each element of that arithmetic progression would have a probability alpha of belonging to A. So we would expect that the average of this thing should be alpha to the k. And so what we get here is that if A satisfies this quasi-randomness condition, and by the way, A UK being close to alpha is a similar thing to saying that something called the balanced function, that's just the function fx equals ax minus alpha, has a small UK norm. And so the way one proves this is just you split A up into f plus alpha. F has a small UK norm. You get lots of terms like this, and then you apply this inequality and so on. But the main point is that what's of interest is that having good control over the UK norm gives you a good idea of how many arithmetic progressions you've got. And if you're trying to prove Szemerédi's theorem and you're trying to find arithmetic progressions, what this does is it gives you a sort of two-case argument. One is the quasi-random case, the case where the UK norm is close to its minimal value, which means that the UK norm of the balanced function is very small. And then the other case is when it's not very small. So when it's not small, you're left with the information that for some smallish constant, f, which is this balanced function, UK, is greater than or equal to some constant. And then you have to decide what you're going to do. And this is what is meant by an inverse theorem. It's meant, you've got some, so we've got two bits of information here actually, so we mustn't forget the one that's f infinity. So it's a bounded function. If you have a bounded function, if it's bounded, then this average is trivially at most 1 in magnitude. So what we're saying is that we're within some constant of the trivial maximum of the upper bound. So this is saying that somehow, even though this c might be a small constant, it could easily have tended to 0, and it will do for random type functions. So saying that we're bounded away from 0 as the size of the group tends to infinity is saying that this UK norm is large. So if it's at least 1 over a million, that counts as large when the group is very, very big. So we want to know what can we say about f. So what happens in Szemerédi's theorem is that if it's small, we're done. If it's large, we find that f has to correlate with something, some sort of function from a very special class of functions. And if you've got that correlation, then you can sort of run some arguments to show that there must be some subprogression somewhere inside which A has slightly bigger density than you started with, and then you can iterate that and get A to have bigger and bigger density to eventually get a contradiction. That's just giving you a very rough idea. That's not the main thing I want to talk about. Just want to sort of explain why these norms are interesting and why inverse theorems are interesting. So an inverse theorem is somehow a theorem that tells you what f must be like. Ideally, it's a necessary and sufficient structural condition on f somehow for it to have a large UK norm. I'll say a bit more about what that means. In fact, I'm going to prove for you. I'll start by just giving you a sort of baby inverse theorem. Let's have an inverse theorem for the U2 norm. So here's the U2 norm. For this, I'm going to need a tiny bit of discrete Fourier analysis. The ground has been very nicely prepared for me by Caroline Terry yesterday, but just in case you weren't here, I'll just do it even more quickly. So also, I use a slightly different notation. If I try to adapt to her notation, I will start writing wrong symbols all over the place. I handled it for me. So I just want to know what is the discrete Fourier transform. I'll do it for two. I could do it sort of abstractly, but I think I'll just do it for two particular groups. So if G is Zn, then I'll define f hat of R to be the average over all x of fx omega to the minus rx, where omega equals e to the 2 pi I over n, which, so I'm not saying it's a zeta n, I'm saying it's omega, so that's my main difference. Also, I like to put a minus there, but that's, again, not very significant. And if G is fp to the n, which is going to be the case of most interest today, then it's almost the same definition. In fact, I would say it's a definition with Hamming distance minimal from the previous definition, because it's just a single point that you have to put there, and otherwise the definition is the same. So this, except omega has a different meaning now. Omega is, in this case, e to 2 pi I over p, and r dot x just means r1 x1 plus rk plus rn xn mod p. And these satisfy rules which I won't go into, but sort of things like convolution law, inversion theorem, Parseval identity, etc., etc. I'll just use those, and you can trust me that I'm using them correctly. And you'll have seen similar things in at least the continuous world, and maybe you've even seen the discrete ones too. So here, why is this relevant? We can first of all rewrite the U2 norm raised to the power 4 as the following. X plus y equals z plus w, fx, fy, fz, fw. So this is x, this is y, and this is z, and this is w. See, this plus this equals this plus this. So there's a one-to-one correspondence between those things. Now I've written it like this. You just see that convolutions have entered the picture. This is the inner product. If you define your inner product using expectations rather than sums, which we do, f star f with f star f. So this is giving us 1 f star f. So sum overall, or take the average over all u, such that x plus y equals u, that would give us f star f of u, and then we have another f star f of u, and so on. And once you've got it in this form, you just say, that's great, we've got things that we know how to translate into the Fourier side, and we get two f hat r's here and two complex conjugates of f hat r's because they're on the other side, we end up with a sum over all r of f hat r squared. And the thing I'm asking you to take on trust, if you haven't seen it, is that we've got an expectation here and a sum there, and all the normalizations are correct, and so on. Sorry, I didn't mean to say squared. I meant to say to the fourth power. Sorry. Very important. And now let's just have a little look at this. That's going to be a completely trivial trivial but important. So there really is an inequality that is not so hard. And on the other side, we can say it's at most there's only very, very slightly less trivial on the right-hand side. And this thing here by Parseval's identity is equal to the L2 norm of f itself, which, because we're assuming f is bounded and defining L2 norms using expectations and things, that's at most 1. So we can just say it's less than or equal to the max of f hat r squared. So that's sort of non-homogeneous inequality because I'm making the non-homogeneous assumption that f is bounded above by 1. So if you've got a bounded function, that tells you that the L4 norm of the Fourier transform is sort of loosely equivalent to the L infinity norm, because the L infinity, so basically if this is small, this has to be small, and if this is small, this has to be small. It's not saying that they're proportional to each other or anything like that, but just if one is small, the other has to be small. Conversely, if one is not small, the other one is not small. In particular, so if this thing here, which is the fourth power of the U2 norm, is not small, that tells us that there must be a reasonably large Fourier coefficient somewhere. If there's a reasonably large Fourier coefficient, that's telling us precisely that this thing here is reasonably large for some r. That's telling us that the function f correlates with the function omega to the rx. And that's the sense in which we have some structure of f. The only way for the U2 norm not to be small is if f correlates with a trigonometric function. And so that is, that's a complete proof of an inverse theorem for the U2 norm. So one might ask, well, what happens with the U3 norm? So let's just say a tiny bit about that. First of all, one wants to think of some examples of functions which have large U3 norm. And so I'll just give you one example that's extremely suggestive. Actually, another one. So, because I'll give you the first one that's suggestive, and then the second one that tells you that the suggestion is not entirely correct. So, the first example is I take omega to the x squared. What happens if I look at this thing when fx is omega to the x squared? I'll get omega to the x squared, sorry, minus x minus a squared, minus x minus b squared, minus x minus c squared, plus x minus a minus b squared, etc., etc. If you add all those things together, what do you get? So what is x squared minus x minus a squared minus x minus b squared? The answer is it's 0. Just check it. It's basically because the difference function of a quadratic is linear, the difference function of a linear function is constant, and the difference function of a constant function is 0. So that's what's going on there. We're sort of somehow taking a difference function 3 times. So that means that this average, in the case where f is omega to the x squared, is actually 1, because every single term is equal to 1. And the same goes not just for omega to the x squared, but to omega raised to any quadratic. So now you can sort of think, well, I think it's pretty obvious what the right conjecture is here, because over here we had that f correlated with a linear function, omega to the rx, or omega to the r dot x. Here we've got a quadratic function. If it's with fp to the end, it would be more like a quadratic form or something like that. So what about, that a function has a large UK norm if and only if it correlates with omega raised to some polynomial of degree k minus 1. It seems like a very reasonable conjecture. Unfortunately, it dies very quickly because there's another example. And I won't say, I'm a little bit vague about this because I don't want to, let's see, I've already used a substantial proportion of my time. So another way of constructing examples that works in Zn is you start in some higher dimensional space, like sort of Z to the D. You take a little box there. You take a d-dimensional quadratic form, which has various sort of values in the box. Use that to sort of define a function f. Sort of raise omega to the power, the values of that quadratic form. That gives you some function, a sort of d-dimensional function. And you take this d-dimensional function and you sort of project it down into one dimension by sort of taking this box and say it's two-dimensional. You might make it look a bit like this. The various rows you sort of put along there, but you give them their two-dimensional values that you got from the function defined on z squared, and then you can have a d-dimensional version of this. And they don't have to be apart like this, they can sort of intermingle to some extent and that sort of thing. It's not obvious, but it turns out that if you get one of these multi-dimensional quadratic functions, it doesn't have to correlate with any pure quadratic function like this, or quadratic phase function. It doesn't have to correlate with any function of the form omega to the, or it doesn't have to correlate well with any function of that form. So it's a genuinely new class of examples because these functions are sufficiently nice that they do still have a large U3 norm. So you've got to take them into account, but they don't correlate with any of these purely quadratic phase functions, and so the sort of nice conjecture is false. So this is what gives the whole area its interest, really. However, one nice thing does happen, and this is a sort of theme that happens throughout additive combinatorics, that things that don't work so nicely for Zn sometimes do work nicely for Fp to the n. And it turns out that the Fp to the n version is actually true, and I'll come back to that. So for Fp to the n, we can't sort of build these extra functions because they sort of turn out to be just the same as the ones we had before. So there we do have a reasonable conjecture. So now let's just say a little bit about what's known. So I'll just say that so for Szemerédi's theorem, it turned out not to be necessary to find a proper full inverse theorem. It was just enough to prove a sort of weak statement, which I won't write down, that says that if you've got a function with a large UK norm, you can pass down to some reasonably long subprogression where you get correlation with a pure degree k minus 1 phase function. And because the whole business is sort of passing down to subprogressions, then that's sort of good enough for Szemerédi's theorem. But it wasn't good enough for Ben Green and Terence Tao, who were trying to prove an extension of their famous result about arithmetic progressions in the primes. They wanted not just to show that they were there, they wanted to know roughly how many of them there were up to n. And that turned out, by a series of remarkable papers, it turned out that the one thing that they really needed in order to complete a program of getting asymptotic estimates for all sorts of linear configurations in the primes was exactly a full inverse theorem for the UK norm, a sort of complete description that would say something like, if the UK norm is large, then f must correlate with such and such that we really understand, a very structured function. I'm not going to say precisely what the statement of the theorem was. So, there's sort of the Green-Tao program to do it, and then the actual finding of the inverse theorem, they involved Ziegler as well. So Ben Green, Terence Tao, and Tamar Ziegler proved a sort of landmark result in additive combinatorics, which, as I say, completed this program of getting asymptotic estimates for configurations in the primes of all sorts of kinds. So that was a sort of huge motivation for inverse theorems. And as I say, the precise sort of description of the structure is not obvious. Actually, finding the statement of the theorem was itself an achievement. So, in the case of the U3 norm, it is roughly speaking that you get that everything must correlate with one of these sort of d-dimensional quadratic type functions for a smallish d. A little bit before that, Bergelson, Tao and Ziegler, perhaps I'll write it like this, but, proved an inverse theorem for the finite fields case, so for the fp to the n case. So their theorem says for all c, there exists a c dash, positive of course. Maybe I should actually say for all c, p and k. And it's not quite true that it's for all p. P has to be bigger than k. I think that's enough. P is sufficiently large, mustn't be very, very low characteristic, such that if fuk is at least c, then there exists a polynomial pi of degree at most k minus 1, such that the corresponding phase function correlates with f. So that says that fp to the n, yes, sorry, I didn't. Yeah, so f is a function from fp to the n to the complex numbers. So here we have a very nice clean statement. So it's tempting to think that the proof should be, well, a lot easier. And in some ways it is. It's cleaner, but this is a very nice situation that we have in additive combinatorics, that there are quite a lot of situations where the thing you started off being interested in was functions defined on Zn or on the integers and so on. And there, as was commented yesterday, you don't have a rich supply of subgroups, and you have to use things like Bohr sets as substitute subgroups, and that involves quite a lot of technicalities, as some people here know very well. And those technicalities go away in fp to the n case, because we've got lots and lots of subgroups. We've got all the subspaces of fp to the n. But somehow the interesting ideas, that's an exaggeration in this case, because there are interesting ideas, genuinely interesting ideas that come in the Zn case that are not present in the fp to the n case. But really a lot of the interesting ideas survive in this sort of technically clean world. So things that a lot of people have sort of said, well, first we work on fp to the n. Once we've got that, we sort of then turn subspaces into Bohr sets and do all sorts of unpleasant stuff. So anyway, we had this theorem of Bergelson, Tao and Ziegler, and something that is common both to the green Tao-Ziegler result in Zn and the Bergelson Tao-Ziegler result in fp to the n, is that they didn't give estimates for c dashed in terms of c. That's because they used the sort of methods that a lot of people in this room like. They're just sort of infinite tree methods. So Bergelson, Tao and Ziegler used a lot of non-standard analysis as a way of sweeping epsilons and deltas under the carpet. They say in their paper that it would in principle be possible to finitize their paper and get a bound which would be extremely weak. That's roughly what they said. So that's a project for a completely mad PhD student. So because understanding the paper is hard enough as it is, and then finitizing everything just in order to get a bound that's sort of an Ackermann function or something is, I don't recommend that one. But so in a way, so now I want to talk about work with Luka Milićević, in which we sort of wanted to find there are two motivations really, and these motivations I think drive quite a lot of people's sort of thoughts on these things. One is, what is the dependence of c dashed on c? And the second question is, what is the right proof of these theorems? There's a sort of feeling that somehow the right proof is yet to be discovered, and that there ought, if you only really understood everything well enough, to be a proof of the level of ease of the proof I showed you for the U2 norm. Somehow you sort of, if you only could think about it in the right way, you just sort of say, oh, I'm expanding in terms of some basis and I get some quadratic phase functions or cubic phase functions or something. It could be that that's just a vain hope. But some people have taken it pretty seriously. And one of them is actually Balázs Szegedi, who was supposed to speak here on Tuesday, I think it was. So he has an approach which would be congenial, I think, to many people here, that involves defining some structures called nil spaces and then passing to some limits of nil spaces and arriving at a sort of asymptotic world where everything is beautiful, then sort of expanding things and so on. But some people, if you're like me, I spend a lot of my time trying to take infinitary things and make them finite. So I'm sort of the opposite. I feel embarrassed to say that in front of this audience, but that's just the way things are. So I sort of feel, so these infinitary things, I want to know what is the right finitary proof somehow. And there are all sorts of reasons to think that's not necessarily an easy thing, especially in Zn. But for Fp to the n, you're not quite sure. Anyway, so what we've managed to do is, I'm not claiming that we found the right proof, because it's a long, complicated proof that I will attempt to convey the flavor of. That's the best I can do, I think, in 20 minutes. But certainly not, I wouldn't go as far as use the word sketch the proof or anything. But we've managed to obtain a bound that's not just an explicit bound, but it's actually what would count in this area as a reasonable bound. It's of the form C dashed is e to the e to the quasi-poly 1 over c. So quasi-polynomial just means e to a polynomial in log 1 over c. So it's roughly doubly exponential in 1 over c. I should have a minus there, otherwise it's a bit too good. I want my minus there, I think. Why don't I just put 1 over the whole thing? Just wherever it really belongs. It was correct, actually, what it was, but anyway. So it's not vastly smaller than 1 over c. Well, it is if you look at things in one way, but given the kinds of bounds that can occur in this sort of situation, it's not too bad. It's not a tower bound or anything like that. So I will now just try to sort of convey, I think the main thing I want to convey, and this I will be able to do, is just that it's a multi-step argument. So if you come away from it thinking, okay, there are quite a lot of steps there, then you've got most of what I wanted to. But I will say a little bit about the first step, because I have to do that in order to make the other steps make sense. So what's our initial assumption? It's that the U4 norm, and by the way, I should say that the U3 norm, a quantitative bound, was okay and known. So this was the first case where there wasn't a quantitative bound known. So what that tells us, so it's a very useful piece of notation for condensing things. I'll define delta AF to be fx of x to be fx fx minus a, and then delta AB f of x is then just delta a of delta b of f of x, which explicitly is f of x, fx minus a, fx minus b, fx minus a minus b, and so on. So this thing here is the average over a, b, c, d, and x of delta a, b, c, d of x. That's one way of writing it. But there are some other ways of writing it. It's also the average over a, b, c of the average over x of delta a, b, c. That should be f. Is that me? Or was it thunder? Anyway. Squared. So why is that? It's because when you expand out this bracket, you get an x and a y. And if you call the y x minus d, you make a little change of variables, and you get back to the formula there. And we can sort of repeat this game. It's also this is not supposed to be, I mean, if you can't see this in your head, again, it's just an easy exercise, and just believe me that it's true. And it's also that. So all those are different ways that we might write the 16th power of the U4 norm of f. And these two are sort of potentially things that one could use for an inductive argument. So here we could say, well, if we know, if this is large, that means that this is on average large, which means that this thing on average has a large U3 norm, and so we could use the U3 inverse theorem to say something about a lot of these functions, difference functions of f. Maybe we can exploit that to get information about f. And that's actually the approach that Green, Tao and Ziegler took in their inverse theorem for Zn. But Luka and I focused on this one here. So we want to say we've got a lot of AB such that this function here has a large U2 norm. And because it's got a large U2 norm, as I've already told you, there must be a large Fourier coefficient somewhere. So for many, many ABs, we can find some R, depending on AB, such that the delta AB f hat of R is large. So from this, we get there exists a function phi such that delta AB f hat of phi AB is large for many pairs AB. So it may be that delta AB f has lots of different large Fourier coefficients, then all I'm doing is just picking one completely arbitrarily. So it's, I can just get some function phi. A sort of more correct proof would probably be to take all the phis at once, but it'd be more sort of canonical, but just do something here that's not particularly canonical. And then the whole thing that makes this have any chance of working, and this goes back also to my proof of Szemerédi's theorem, is that phi AB is to do with delta AB of f, and the delta ABs of f are sort of difference functions of the same function, so we might expect them to have various relationships, and not, the phi couldn't just be any old function. And that turns out to be true in a quite strong sense. And that strong sense, in this particular context, whoops, wrong one. In order to say one nice property that f has, I need a little, one quick definition. I'm going to define a vertical parallelogram to be a set of points in fp to the n of the form xy, xy plus h, x plus w, y dashed, and x plus w, y dashed plus h. And h we call the height of the parallelogram, and w we call the width of the parallelogram. They're not heights, and I mean they're just elements of fp to the n, but when you're drawing pictures, they're the height and the width of what you've drawn. And also I'll define a 4 arrangement. So that's a vertical parallelogram. A 4 arrangement is, oh, this thunder, I've worked out what it is, it's the blackboards. Anyway, it's a pair of vertical parallelograms of same width and height. And I don't want to use the fixed board, because I'll have to cover it up. Now the idea is that, supposing phi, what we're going to try and find in phi is what we think of as bilinear structure. So we're going to try and show that phi is somewhat bilinear. There are reasons I won't go into to expect in advance that this will be the case. Now, if phi were a bilinear function, we would get that, it's another easy thing to see, that phi xy minus phi xy plus h minus phi x plus wy dash plus phi x plus wy dash plus h would depend only on w and h. Just can see that in your head, really, because that minus that just depends on x and h, and this one only depends on x plus w and h, and then when you subtract in the other direction, you get something that depends just on w and h. So we say that phi respects a Fourier arrangement if, and yet another of these things with phi mu minus phi, whatever the last thing is, equals 0, which is just a way of saying, perhaps I could just say, well, define psi of WH to be phi of xy minus phi xy plus h minus phi x plus w y dash plus phi x plus w y dash plus h. If phi is bilinear, then that's a well-defined function. So what we'd like is to sort of somehow show that it's not too far off being well-defined. And so we say phi respects a Fourier arrangement if at least psi is well-defined for those two vertical parallelograms. It takes the same value on this one as it takes on this one. So I haven't really written this definition very well, but if what I really do to make it formal, I say psi of phi of a parallelogram is this thing, and then if I've got two vertical parallelograms of the same width and height, and phi of this one is equal to phi of this one, then we say that phi respects the Fourier arrangement. So there's a step. All that was really step one. So there's a step that says phi respects lots of Fourier arrangements. And lots always means within some constant independent of the size of the group of some trivial maximum that you can work out. I won't say that's, again, lots of sort of Cauchy-Schwarz and that sort of thing. Then there's an argument that uses a technique called dependent random selection, which I just say just for the benefit of the few people here for whom it will mean something. Roughly it means choosing things at random, but not independently at random, but choosing dependencies in a sort of suitable way to make nice things happen, that we can get to a subset such that phi respects almost all Fourier arrangements. And almost all is what additive combinatorialists call 99%. So it means it's a constant that you can make as close as you like to 1, but it's quite important. It's not allowed to depend on the C, which you start with, but that's just a slightly technical point. Yes?
Respects for arrangement, do you mean depends only on W and H instead of equal to 0?
What I mean is that if I've got two parallelograms here, and I define phi of this, minus phi of this, minus phi of this, plus phi of this for this one, and then the same thing over here, then 99% of the time I'll get the same answer for the two parallelograms.
So the exact sense is not equal to 0 in the first line you wrote? Or
0 just meant that what you get here minus what you get here equals 0. So it's saying the two things are the same. So that was supposed to have 8 terms in it. That was not clear from what I wrote. Because it had 8 terms, the only clue that it had 8 terms was that I couldn't be bothered to write it out, whereas I could be bothered to write this one. But sorry about that. That wasn't perhaps enough of a clue. Now, actually, we need something more than just Fourier arrangements. We need what I call second-order Fourier arrangements. And these are things where you take vertical parallelograms, you take 8 of them, and the 8 vertical parallelograms, you then look at their widths and heights, and their widths and heights form a Fourier arrangement. See what I mean? So it's so in fact, We get the same thing for second order Four arrangements. So we do this step of second order ones, and then we pass to a subset such that phi respects almost all of them. You can work out what it means to respect almost all of them. You've got all the different values that you get on those, all those parallelograms. That gets you some functions that are well defined on the widths and heights, and then you put all those together into two vertical parallelograms, etc. And then you've got to get the same thing out at the end. Once you've got this, we get that psi, a sort of induced function, that's the function that you get by psi of w of h is phi of this plus phi of this minus phi of this minus phi of this. So psi respects, I'm not going to say precisely what this means, but almost all first order Four arrangements on the mixed convolution of A. And I think I haven't got time to write down what it is, but the idea is that you take the characteristic function of A, and then in each column, so to speak, you take its convolution with itself. Once you've done that, then in each row you take its convolution with itself, and that gets you a mixed convolution. So it's a horizontal convolution of vertical convolutions. That's where the word mixed comes in. You can see there's a sort of relationship between this. When you do a horizontal thing, that gets you two values that are in the same row, and then you can do a sort of, sorry, when you do a vertical one, and then you can do a horizontal one. And then there is, we need to get some sort of information about what mixed convolutions look like. And this is a bilinear generalization of a very useful tool in additive combinatorics. It's called Bergelson method. A bilinear Bogoliubov. I should just mention that work very closely related to this bilinear Bogoliubov step. They're not quite identical to the one I'm talking about here. Was done by Pierre Benvenu and Ley, who also proved recently and independently a bilinear Bogoliubov theorem. Anyway, the bilinear Bogoliubov thing tells us about the structure of mixed convolutions. And roughly the structure is this, and this is, I think, has some sort of tiny points of contact. Supposing I've got what it says is that if you've got a function, and you take its mixed convolution, so you convolve in respect to one variable, then convolve with respect to the other variable, can be approximated in L2, that's for the purists, by a function that is constant on level sets of some bilinear function from fp to the n to fp to the k, where k is small. So you can find a small k, you can find a bilinear function from fp to the n to fp to the k, and then you can approximate f by a function that only depends on the value taken by beta. So there's sort of level sets of beta, it's roughly constant. So this sort of has a flavor of an arithmetic regularity lemma, except that we've done this mixed convolution. So we're not starting with an arbitrary function, but nevertheless, maybe there's something to be said there. Unfortunately, even this outline, I think I'm not going to be able to complete. But maybe I can allow myself, I started 2 minutes, okay, I get 2 minutes. So how can I say this very quickly? By all sorts of averaging, we get that psi respects almost all Four arrangements on a level set, on just one level set. And then there's a stability theorem that says that psi can be approximated by something where this almost all turns into all. So approximate, this is not the model theorist's use of the word stability, in case you were salivating too much. It's approximated by psi dashed with, for all replacing almost all, And then there's an extension theorem that says, under a certain rank condition, which I won't go into, can extend psi dashed to the whole of fp to the n squared. Since I've run out of time, there's something that's nice to show the details of, but I think I'll just have to ask you to trust me that once you've got that, we've got this genuine bilinear behavior that closely relates to what we had before, we've somehow got where we've got that the function phi has a bilinear behavior. When you expand out the expression that the arrow is pointing to, well, you get average x, a, b, c of delta a, b, c, f, x, omega to the minus tau a, b, c, where tau is a trilinear form. The trilinear form comes from taking the bilinear thing we've got here and taking a dot with a c. So it just some manipulations get you to here. If you could assume that tau was a symmetric trilinear form, which it turns out you can, but that's a non-trivial thing to say, then it decomposes by a sort of polarization identity into kappa x minus a, etc., etc. Then you can define gx to be fx omega to the minus kappa x, where kappa is a cubic polynomial. And so you get that this thing, then what we end up with here is just the u3 norm to the 8 of g being large. And when the u3 norm of g is large, the quadratic inverse theorem tells you that this thing correlates with a quadratic, omega to a quadratic. Since that's just cubic, it tells us that f correlates with cubic. So I did just about get to the end of the whole thing. And I must stop. So. Well, for us, we were just doing 4, so there's no dependence on k.
So it's only the proof of
k equals 4, yes. Yes, so I didn't make that clear, but we just wanted to do the first non-trivial case, which I hope is sufficiently non-trivial. P, I think the dependence on P is not too important, but I haven't checked out all that carefully. I should say that I have a slight sort of awkward feeling in my stomach about what the dependence on k will be, because just of this very last thing, exploiting the quadratic inverse theorem. Because by the time we got to here, we've already introduced a couple of exponentials. So the bound that we get, the lower bound we get for this, is considerably worse than the lower bound that we had for the original thing. So I have a horrible feeling that for the k, each one is going to introduce exponentials. So the dependence on k, if we can get this to work in general, might unfortunately be a tower without extra ideas. No, we're very much regarding p as fixed and n tending to infinity. Sorry, I should have stressed that much more. Yeah. And I should also say the theorem is known, it's known to be false for p very small. P equals 2, it's false, but there is a modification of it using something called generalized polynomial phase function as well that is true. So there's a suitable adaptation of it, though we haven't worked out whether we've got a quantitative version of that. Meaning we haven't, but we don't know. It might be possible at some stage.
Other questions? You said that most of things work for FPTN, which don't work for ZN. Is this to do with bounded exponents? I guess that they're the bounded exponents.
Yes, I think it's very closely related. So it's just, it means that we have all sorts of subgroups around, and I don't see I think in principle this could perhaps transfer to a Zn proof, but that it might be rather unpleasant. Well, I know it will be. Let's just. Actually, I wanted to mention just briefly a former co-author, Julia Wolf, gave a hollow laugh at that point. One of the ideas that went into my very quick remark that this made symmetric is the idea that you can approximate Tor by sort of give a low rank approximation. It's not at all clear what low rank means for a trilinear form, but it uses a notion of analytic rank that came up in some, that she and I came up with in some work that's all sort of somewhat related to this kind of area. Yeah, so just converting subspaces into Bohr sets, or something called regular Bohr sets, lots of times is very, very tiring. So, yeah.
Any other questions?